Today we are going to discuss numerical problems and their solutions. So, let us try to solve few problems. Problem number 1, a lap of 400 kilotex is being opened by a Likarin of 10-inch diameter. Read the problem carefully. The surface speed ratio between Likarin and feed roller is 1000. The Likarin has 6 lakh teeth on its surface. Okay. What will be the average weight of tuft on its teeth, that is on Likarin's teeth? This is one question. The other one is, if the lap is made of 3 denier 40 millimeter fibers, what would be the number of fibers per tooth? So, there are two questions related to this problem. Read the problem carefully and now try to solve it. So, what is given here? The weight of the lap in terms of its linear density 400 kilotex. The other parameter given is the diameter of the Likarin, which is 10-inch. Third parameter given is the surface feed ratio, that is the draft between feed roller and the Likarin, which is 1000. And the fourth parameter given is a number of teeth on the Likarin surface, which is, let us say, 6 lakh teeth are there. About the fiber, what is given? The fiber dimensions in terms of its denier value and length. So, these are the parameters given in the current problem. So, let us see the solution now. Okay. So, the lap linear density has been given, which is 400 kilotex. That basically means it is 400 gram per meter, that is 1 meter of lap will weigh 400 gram. All right. The next point is, what is the circumference of the Likarin? So, we have to multiply the diameter of the Likarin by pi. So, 10 multiplied by 3.14 will be the circumference in inch. We multiplied by 2.54, that becomes centimeter, and if we divide it by 100, we get it in meter, and the value is 0.79 meter. Now, we have to find out that if the Likarin rotates by 1 revolution, how much length of lap is fed? What is given here is the draft, which is 1000. That means, if for 1 revolution of the Likarin the surface moves by 0.79 meter, the length of the lap that will be fed will be 1000 times less. Hence, length of lap fed per Likarin revolution is going to be 0.79 by 1000 meter. All right. Now, go to the next step. What is the weight of fiber fed per Likarin revolution? If we know the length of lap and we know the linear density of lap, that is gram per meter in its weight, if we multiply these two, then we get the weight in gram. So, that much fiber is fed to the Likarin per revolution of the Likarin. So, we convert it into milligram, we get in milligram. Next, how many teeth are there on Likarin? There are 600,000 teeth, which is also given. So, average tuft weight per tooth is going to be 316 divided by 600,000 in terms of milligram, and we divide 316 by 600,000 and we get the value 5.26 in 10 to the power minus 4 milligram. So, that is the average tuft size per tooth on the Likarin. So, this gives you the answer to the first questions let us go back and see what is the first question which was given. They asked what will be the average weight of tuff on its teeth. So, this answer we have received. Now, let us go to the second part. Once we know that so much milligram of fibers are there per tooth on an average, if I want to find out how many fibers are there per tooth. So, what we need to know now is what is the weight of a fiber, of a single fiber. So, weight of one single fiber is, we know the denier value of the fiber and we know the length of the fiber. When 3 is the denier value of the fiber, that means 9000 meter of fiber weighs 3 gram, and hence the weight is going to be 3 by 9000, that is the meter. Meter you convert it into millimeter, we multiply it further by 1000, and that we multiplied by 40, which is the length of fiber, and we get what is the weight of a fiber, which is around 1.33 in 10 to the power minus 5. That is the weight of a single fiber. So, now how many fibers are there per tooth? We take the ratio, the weight of fiber per tooth and the weight of a single fiber. If we take the ratio, we get a value 39.5, which is roughly close to 40, and hence we can say that on the Leykanen tooth on an average there will be 40 fibers in this given situation. The kind of parameters that we have given in this particular example, we can say roughly there will be 40 fibers per tooth on the Leykanen. This is how we have to logically approach to the problem and find out its solution. All right. From here we go to another problem. Whenever a problem is given, you must read the problem twice at least, and then you start thinking how to approach to get a solution. This problem is very simple. If a card production rate is 60 kg per hour, how much time it takes to consume a 40 meter lap of 500 kilotex? It is a very simple problem. So, the length of the lap has been given and the linear density of the lap has been given. That means, we will be able to find out what is the weight of a particular lap if I know the length and if I know the linear density of the lap. So, if I know the weight of the lap and if I know the production rate of the machine, then we can easily find out how much time it takes to consume the entire lap by the machine. Okay. So, let us go now. Solution: lap linear density is 500 kilotex. That means, it is 500 gram per meter. 1 meter of the lap will weigh 500 gram, that is half a kilo. This is the typical linear density of the lap. So, weight of a full lap is going to be 40 into 500. So, 20,000 gram, that means it will be around 20 kilo, that is the weight of a single lap. So, time taken by the card to consume this entire lap, if there is no interruption of the machine, then it is going to be 20 by 60 hour. We convert it into minute multiplied by 60. So, we get 20 minutes. That means, in 20 minutes this lap of 20 kg will be consumed by the machine, provided there is no interruptions. The machine is working with full capacity and there is no stoppage. Okay, this is a very simple problem. Now, we move to the third type of problem. Now, this problem, before we actually get into some numerical problems related to cleaning, that is combined cleaning, let us try to understand how to find out cleaning of two machines working in succession. That is, how do I find out the combined cleaning of two units if I know the cleaning of individual unit. So, let us say here is a machine where the trash content in the input material is around T. Cleaning unit 1 is cleaning efficiency is E1. The trash input to the machine is T. Therefore, the ejected trash is going to be T into E1 by 100, okay, and trash that flow forward to the next machine will be how much? Is going to be 1 T minus T into E1 by 100. That means, if I take T common, it will be T into 1 minus E1 by 100. So, this is the trash that flows to the next machine. So, this much is removed and this much goes to the next machine, which is the cleaning unit 2. And let us say the cleaning unit 2 has a cleaning efficiency E2, not E1, E2. Now, what will happen? That this machine is also going to clean the trash which is being fed to it. Cleaning efficiency is E2. Therefore, the trash that will be ejected is going to be T into 1 minus E1 by 100 into E2 by 100. That is what will be removed by the machine, and which will flow back is what was the input and what is the output trash. Difference between these two is going to be the trash which will flow forward. That means, trash left after this is going to be T into 1 minus E1 by 100 into 1 minus E2 by 100. So, this much trash will flow forward. So, what is shown at the bottom is this trash getting ejected, and what is moving forward is also shown in the diagram. So, dash at each and every step the machine is cleaning the material, part of the trash or impurities which are there is falling down or being extracted, and the rest is moving forward. Now, if I want to know what is going to be the combined cleaning efficiency of the cleaning units 1 and 2 together, this kind of situation arises in the case of, let us say, blow room and carding machine combined cleaning efficiency of the two sets of machines, that is blow room machines and carding machines. What is the combined cleaning efficiency of blow room and card? So, cleaning unit 1 suppose representing the blow room and cleaning unit 2 representing the carding machines. So, and we know the individual cleaning efficiency from our past data. If this is the situation, now if we want to find out the combined cleaning efficiency, how to go about it? Total trash that will be removed is the trash which was fed T minus the trash that has moved forward. So, what we see here that T into 1 minus E1 dash, what is E1 dash and E2 dash, we must first try to be clear. E1 dash and E2 dash representing the fractional cleaning, that is E 1 dash is nothing but E 1 by 100. Similarly, E 2 dash is nothing but E 2 by 100. Cleaning efficiencies are generally expressed in terms of percentage. So, suppose as an example, cleaning efficiency of a carding machine could be 85%. So, if say if E 2 is 85%, then E dash 2 is going to be 85 by 100, that is 0.85. Therefore, E 1 dash or E 2 dash is representing the fractional value of the cleaning efficiency. So, trash removed is T into T, trash removed will be this plus this, that is T into E 1 by 100 plus T into 1 minus E 1 by 100 E 2 by 100. If I add these two, also we can find out how much trash has been removed, or the other way is how much trash has been left or in the material. If we know this and we subtract it from the original trash, then also we can find out what is the trash left or trash ejected. So, we are following this procedure, that is how much trash has flown forward is this value, original trash is T. So, difference between these two will give us how much trash has been actually removed. Once we have this value, next is the definition of cleaning efficiency, that is trash removed by trash in the input into 100. So, trash removed, if we take T common in the above equation, then we get this equations. The expression is T into 1 minus E 1 dash into 1 minus E 2 dash. So, that is the trash which has been removed, that divided by original value of trash in the input. So, we divide this by T and that multiplied by 100 will give me the combined cleaning efficiency. So, if we do this, T and T will cancel and we will be left out with the expression C combined is 1 minus E 1 dash into 1 minus E 2 dash, and if we want to express in percentage, we multiply it by 100 and we get the combined cleaning efficiency in percentage. So, this is how we can find out the combined cleaning efficiency of two machines. The final formula is easy to remember, that is cleaning efficiency of machine 1, cleaning efficiency of machine 2, if they are already known. Therefore, what we will do? We found out what is the cleaning efficiencies of these machines divided by 100, we will get decimal figures, 1 minus that decimal figure into 1 minus decimal figure of the next machine, multiply them together and we subtract it from 1, and that multiplied by 100 will give you the combined cleaning efficiency of the two machines. This is how we can find out the cleaning efficiency of two machines. We may also face a situation where instead of two there could be multiple machines. Let us say in the blow room type machine. Sometimes in the blow room there are required maybe 2 opening cleaning units, or there could be 3 opening cleaning units, and we want to study what is the combined cleaning efficiency of the entire blow room when individual cleaning efficiency of the cleaning equipments are known from past experience. Or do we want to know, I want to find out the efficiency of an intermediate machines when the efficiencies of the other machines are known to us. So, that kind of situation may also arise. So, I have taken another example where there are 3 machines in succession. The procedure to be followed is exactly same, there is no difference. So, cleaning unit 1, cleaning unit 2, cleaning unit 3 in this case, trash ejecteds are shown at the bottom and trash flowing to the next machine is also shown at the top. So, this is how the trash is flowing, how much trash is left and flowing along with the material is shown. What is there up to this machine is given here. So, the steps are exactly same and we look at this, that is we first changes the value E 1 to E 1 dash, E 2 to E 2 dash and E 3 to E 3 dash, that is these values are normally given in percentage term. So, we divide by 100 and we get the value E 1 dash, E 2 dash, E 3 dash for 3 different machines. So, total trash ejected is exactly going to be the same as was shown earlier. It will be T minus T into 1 minus E 1 dash into 1 minus E 2 dash into 1 minus E 3 dash, because there are 3 machines are there. So, if I take T common, I am left out with this. This is what is the trash that has been removed by the 3 consecutive cleaning units. So, combined value is going to be, the definition wise it is trash removed by trash input. So, we go by the same logic and we can say that the combined cleaning efficiency is going to be in this case T into 1 minus the numerator represent the trash removed, denominator is the trash in the input, we take the ratio multiply by 100, T and T cancel each other and we are left out with the numerator multiplied by 100. That gives you the cleaning efficiencies of 3 machines working in saturation, and that is how we can easily find out the combined cleaning efficiency of 2 units or 3 units or 4 units or maybe n number of units. The procedure is exactly same. Okay. Let us say now a problem. Read the problem carefully again. The blow room and the card cleaning efficiencies are 60% and 90% respectively. So, 2 cleaning units, blow room is one of them and card is the other. Cleaning efficiencies of the 2 machines are given. If the trash present in the card sliver is 0.08%, what was the trash level in the bale? So, bale is the input to the 2 cleaning units, blow room and card. So, input trash level is not known to us, that is what we have to find out. The output trash level is given in terms of percentage. Now, think for a few minutes and then try to solve the problem. Okay. So, let me start because we do not have so much time now. What is given is the cleaning efficiencies of blow room and card. So, E 1 represents blow room and E 2 represents card. So, what is E 1 dash is 60 by 100. So, that is 0.6. What is E 2 dash is 90 by 100, that is 0.9. So, we have written E 1 dash 0.6 and E 2 dash 0.9. Let us say the trash in the bale is T percentage, which is unknown to us. This is the input trash. Trash in the output material, that is card sliver, has been given, which is 0.08%. So, trash that has been removed by the 2 machines T minus 0.08, that is why the trash has been removed. We do not know what is the value of T. as of now. Okay. Trash removed is T into E 1 dash plus E 2 dash minus E 1 dash into E 2 dash. That is, if we simplify the previous formula that was shown earlier, we can get these expressions of trash which has been removed. So, in this case, trash that has been removed will be T into 0.6 plus 0.9 minus 0.6 into 0.9. So, if we add 0.6 plus 0.9, I get a value 1.5, and when you multiply 0.6 and 0.9, we get 0.54. So, if we subtract these two, we get 0.96, and hence trash that has been removed by the two machines is T into 0.96. Whatever was the trash in the input material, 96% of that actually has been removed. That means it is T into 0.96. If this is true, so now we can write that T minus 0.08 is T into 0.96. Okay. So, from here we have to find out what is the value of T. So, we bring T on the left hand side and the constant part on the right hand side. This is a simple equation now, and we take T common, okay, and now we can find out what is the value of T. This is going to be 0.08 by 0.04, that is 2. That means, the level of trash in the input, that is in the bill, was 2%. Okay. So, this is how this simple problem can be solved also. More complex problem could be there. So, we will also see later on. So, you start thinking about how to apply the concepts in solving the problems. Now, let us take another problem. This, what is this? The actual draft in a card is 90. Okay. So, actual draft, this word is important. The mechanical draft is 85. So, you have already learnt that draft in the cardiac machines could be two types, one is actual and the other one is mechanical. You have to recall what actual means and what mechanical draft means. Actual draft means, actual draft is determined on the basis of linear densities of input and output material. That is, we take the ratio of linear densities of input or output by input, depending upon in which methods we are expressing the linear density of the input and output material. If it is in text system, the linear density of the lab divided by linear density of the sliver will give you the actual draft. So, in this calculation, the gears and the speeds, they do not come into the picture. We only see what is the linear density of the input and what is the linear density of the output. We are not bothered about the speeds of different organs of the machines. That is what is actual draft. And the mechanical draft, if I again repeat, mechanical draft is based on the speeds of the input and output organs of the machines. So, here in the calculation of mechanical draft, we need to know the speed of the elements, or we have to go through the gears and pulleys of the machine to find out what is mechanical draft. So, what we see in this case, that mechanical draft is less than actual draft. This is one point you should also remember. This is always true for carding machines, that mechanical draft will be less than actual draft, because the waste extractions. We have given here the waste percentage extracted by the card will be how much, that is what we need to know. Why the mechanical draft is less? Because the machine is going to extract some waste, some material will fall on the Likert and some material will go to the flats and some material is going to fall below the cylinder. So, this is the loss of material while we process the fibers. So, we need to know from this two values what is the waste that has been extracted by the machine. Okay. How to solve this problem? The extraction is waste means the material is actually thinning, because some mass is being removed. So, whenever there is a thinning of material being fed, we say that there is a draft, there is some stretch in the material. So, generally through stretch we apply draft and we make the material thinner and thinner. We can also make a material thinner by removing part of the material from its flow. So, in a way waste extraction is acting as a draft, as if, and trying to make the material thinner. Okay. So, how to go to solve this problem? So, I am going to the next slide now. This relationship was also told to you earlier, the relationship between actual and mechanical draft in the case of carding machines. Actual draft is mechanical draft into 100 by 100 minus waste percentage. This is what you have to remember. So, mechanical draft multiplied by 100 minus waste percentage will give you the actual draft. So, if we look at this formula, then what we find, actual draft is given already, mechanical draft is also given, and what is not given is waste percentage. So, if I substitute the values of actual draft and mechanical draft in this particular relationship, we can easily find out what is the waste percentage. So, that is what exactly we have done. Actual draft is 90, mechanical draft is 85, waste percentage is something is not known to us. So, now we have to, from this expression we have to find out what is the waste percentage. These steps are shown. 100 minus waste percentage is going to be 85 into 100 by 90, 94.4. Therefore, waste percentage is going to be 100 minus 94.4, which is 5.6. So, waste extraction by the carding machine in the present case is 5.6%, and because of the waste extraction the actual draft was more than the mechanical draft. If we waste percentage is 0, let us say, if we look at the expression at the top and put the value of waste to be 0, what we get? 100 by 100 minus 0, this part of the expression becomes what? 100 by 100, hence it becomes just 1, and therefore, actual draft becomes equal to mechanical draft. So, machines where there is no waste, in those machines actual draft and mechanical draft will be almost same. So, there are machines where waste extraction is almost negligible, and therefore, in those machines it will not make much of a difference between the actual draft and mechanical draft, they will be almost similar value. We will see that in while discussing some other machines where waste extraction is almost 0. All right. So, this is the problem we have solved now. From there, we take up another problem today. A doffer of 27-inch rotating at 30 rpm is producing a sliver of 5 kilotex. Okay. The cylinder speed is 300 rpm. So, these are the parameters which are given. What is the production of the card per cylinder revolution? We need to know the answer. The answers are stated here. We have to find out how to get these answers. Okay. What is the production of card per cylinder revolutions? How to go about it? First, we have to find out from the given data what is the production rate of the card. So, first from the given data we can find out how much sliver is being produced by the carding machine per minute, that is based on the rotational speed of the doffer. In this case, since the doffer diameter and speeds are given, for all practical purposes we will assume is a doffer which is actually producing sliver and delivering sliver. So, whatever is the doffer surface speed, that is going to be the delivery rate from the machine. So, production of cars in terms of surface speed of the doffer we have to find out. So, pi into 27 into 2.54 into 30 divided by 100 to get it into meters per minute, that is the delivery rate from the machine. So, we call it production of the card in terms of meters per minute of sliver. So much sliver in terms of 64.6 meter of sliver is produced per minute from the machine. All right. Now comes what is going to be the production. That is, what is going to be the weight of this sliver that we produce per minute. So, production is going to be how much is 5000, 5 kilotex is the linear density of the sliver. So, 5000 divided by 1000, that is going to be the gram per meter of the weight of sliver. So, per meter of sliver we will weigh 5000 by 1000, that is 5 gram, and that multiplied by 64.6 will give you the weight of the sliver that will produce per minute. So, it is 323 gram of sliver is produced per minute by the machine. So much material is produced per minute. The production per cylinder revolution we need to find out. So, we produce 323 gram per minute. So, cylinder revolution is speed has been given as 300. Therefore, production per cylinder revolution is going to be 323 by 300, hence it is going to be 1.076 gram. That is the production per revolution of the cylinder. Okay. So, this is the solution to one problem, one questions that was there. What is the next? If the transfer efficiency from the cylinder to dropper is 0.20, what will be the load on cylinder? Okay. Let us go to this now. How much is going to be the load on cylinder? The load on cylinder is going to be the whatever is produced per cylinder revolution divided by the transfer coefficient. So, transfer coefficient is actually in this case 0.2. In terms of percentage, it is 20% that has been given. So, if I per revolution if I produce 1.06 gram of sliver, that means that much material is transferred from cylinder to doffer per revolution of the cylinder. So, that divided by 0.02 not 0.2 0.2 will give you 5.38 gram. That means, the fiber load on the cylinder is going to be 5.38 gram, that is what is going to be the load on cylinder. All right. And third thing is, if this is the gram of material lying on the cylinder, what is the linear density of the material which is there on the cylinder surface. So, cylinder circumference we have to find out. So, we apply the formula pi d, pi into diameter of the cylinder 50 inches multiplied by 2.54 becomes in centimeter, that divided by 100 gives you the circumference of the cylinder in terms of meter, which is 3.9878 meter. All right. So, the material which is there on the cylinder surface is 5.38 gram. Total circumference of the cylinder is 3.9878. So, if we take the ratio of these two, we get gram per meter. So, we divide these two and we get 1.349 or 1.35 gram per meter, that is the linear density of the material on the cylinder surface typically. Now, this material is spread out, because if I try to find out what is the fiber load per unit area on the cylinder surface, that has not been asked, but suppose you are interested to know this, that is how much material is there per unit area of the cylinder. What we should do in that case? I know how much material is there on the cylinder, that is load on cylinder per revolution of the cylinder is 5.38 gram. If I know the total surface area of the cylinder, then I divide 5.38 by the total surface area of the cylinder, and we will get the actual fiber load per unit area of the cylinder. Or we can say that 1.35 kilotex material which is there, this is gram per meter, that has been spread out over the entire surface area of the cylinder, and therefore, there is a thin layer of fibers on the cylinder surface which is fiber load, and as we have discussed earlier, where this load of fibers on the cylinder surface has a very it plays a very critical role in deciding the quality of the carding machines, quality of the carded sliver, because if the load is too much, the opening or separation of fibers is going to be affected. There could be chance of nap formations, cluster may not get opened out. So, we will get a sliver which is full of naps, or there are many clusters of fibers which will be visible to us when the yarn is made. Okay. Now, this is another problem, that is, let us take this is the last problem that we are going to discuss today. The production rate of a card is 50 kg per hour. The waste level under Likarin and flats are 2% and 1.2% respectively. How much waste is extracted in a day of 22.5 hours of working? Okay. If the cost of cotton is 90 rupees a kilo, how much is the loss due to waste generation in the card? So, two questions have been raised and we have to find out the answer. The card production rate has been given, the waste generated at two different places are also given. The time of working in a single day also has been given. How to find out how much waste we create or the machine is creating in the whole day. Whole day means not 24 hours, but 22.5 hours. Solution: What is the total waste? 2 plus 1.2, that is 3.2%. Very simple. Waste generated per day will be how much? How much waste we generate first of all per hour? If I produce at the rate of 50 kg per hour, waste generation will be 50 into 3.2 by 100, it will be 22 multiplied by 22.5, that will give you the total waste per day. It will be around 36 kilo, that is the waste that is generated. And loss which will be there per day 36 into 90, because this is the waste of fibers which we generate, that was already bought at the rate of 90 rupees per kilo, and hence loss due to this waste will be rupees 3240 per day. If I want to find out the loss for the whole year, though it has not been asked, I multiplied it by 365, and that will give me a figure this. So, you can see that in a car whatever waste that is generated, here we get a figure 11,82,600 rupees. We are ignoring these waste, part of it, this waste can be also be sold out and we can fetch some price out of it, but the only idea giving this figure is that we must appreciate that the possible loss which we incur when we generate waste by the carding machines or by the blow rooms, and hence in a mill people will be always very careful about the quantity of waste that different machines are generating. Okay. So, from there we stop today's discussion and thank you.